Welcome to lecture 27. In this lecture we're going to apply what we've learned so far by solving the same problem twice. We're going to solve it in two ways. The problem we're looking at is a box that's sliding down a ramp. And unlike previous times when we had this, now there's friction involved. And actually, you were able to solve this problem with friction a long time ago, and you probably did so at one point or another. So we're just going to review how to do that using forces in Newton's second law. I'm going to find the speed at the bottom. But then we're going to rework the same problem, and this time we're going to use energy and work. And hopefully in the process you'll see how those two ways are equivalent. So we're going to solve it the first time using forces and a bit of kinematics. Because forces only tell us about acceleration, and we want to find the final speed. And then we're going to use work and energy to solve the same thing. And I have supplied values here, 0.2 for the coefficient of kinetic friction, 20 degrees for the angle, and we start at a height of 6 meters. But really, I want to solve this symbolically, and we can just plug in numbers at the end. Let's get started with the first method. This is the first method using forces and kinematics. Well, what forces do we have? The box and the ramp, you know how to deal with it. This might be a good review, so maybe you should pause the video right now and try to work the problem yourself. Well, if you've done this, you can keep watching. There's a weight, and the weight is of course mg, because the Earth doesn't care what we do, it pulls with a certain force that's given. Then there's a normal force, and normal force, if my hill is like this, right, the normal force acts in this direction here. Again, that should just be a review for you. I'm going to call this F subscript n for normal force. And now there is friction. The friction, well, if the thing is sliding down, like without friction, it would start sliding down this way. So that tells me that friction must be in the opposite direction, right? Because it's sliding down. So there's kinetic friction. I'll call this F subscript K for kinetic friction. Okay. So the downhill forces then, well, this one doesn't apply any downhill force because it's normal force, it's perpendicular to the hill. But we've got a component of the weight, and hopefully remember how to do this. Let me call this the x direction and this the y direction. Well, in the x direction I have, what do I have in the x direction? I have that mg sine theta, and if you're not sure where it comes from, review the earlier lectures on forces and taking components and motion down a ramp. That's the weight down the hill. I'm going to subtract from that the friction. The friction is of course the normal force times the coefficient. Mu K, kinetic friction, times the normal force. And that's, is it equal to 0? No, this thing is accelerating, so it's equal to ma. A is not 0 here. Now the normal force, hopefully you remember, in this kind of situation I can analyze the y direction. This is equal to mg cosine theta. And I'm just going to write y like this in the y direction. That's again analysis we've done before. So it should come easy to you. Let's put the pieces together. I have mg sine theta minus mu k times mg cosine theta is equal to ma. I can cancel out the m's. And well, I just have that a is equal to g. I'm going to factor out the g. Then I have sine theta minus mu k cosine theta. It's my acceleration. But now I want to go down a certain distance, right? I want to figure out the speed at the bottom of the ramp, and the ramp goes from here to here. Let's give the ramp length a name. Let's call it L. Then I can now find the final velocity, and maybe you want to review your kinematics if you're not sure how to do that. I want to use the final velocity squared. It's the initial velocity squared, which is 0, starting from rest, and then twice a times the change in the displacement. Well, I've got values for that. G sine theta minus mu k cosine theta. Now, what is my delta x? Well, delta x is just L, the length of the ramp, right? Goes from here to here, and this is my x direction. But what is L? Well, I can look at this. I know the height is 6 meters, and so I can look at this sort of triangle here, and it tells me that h would be L times sine theta, so L is h divided by sine theta. So, write this down. I'm going to plug this in here. And that allows me to then plug in, put it all together, and I get that this is 2gh sine theta minus mu k cosine theta divided by sine theta. I can leave it like this. Then I can plug in some values. And I think if you plug in the values given in the original problem, right here, height 6 meters, mu k 0.2, theta being 20 degrees. Notice I don't need to know the mass of the box. I had to include it, but it actually cancelled out. So, and I don't know it, so it's just as well. If you plug in the values, plug in g is 10, I am getting 54.06 according to my calculation, meters squared per second squared. That is v squared. So I'm going to take the square root. V final is equal to 7.35, I think, meters per second. Right, so that's my speed at the bottom, solved using forces and then a little bit of kinematics. And again, this should just be a review, right? You should be able to do this in this way. But now let's try another way. And I'm not saying the other way is faster. Sometimes it can be, sometimes it might be slower. But now we're going to use work and energy. Let's look at the box at the top. What energy does it have? Well, it is sitting there, but it's a certain height, so it has gravitational potential energy. So it's our second method, using energy. So at the top, it has gravitational potential energy equal to its mass times g times the height. What did we call the height? Oh, we called it h, so I can actually literally write mgh the way you remember it, right? Because I've used h for the height, and I'm saying my ground level is going to be the 0 height. Of course, that's a choice. My kinetic energy at the beginning is 0, because we're starting from rest. At the bottom, and I'm leaving a gap in here for a reason, I have gravitational potential energy. Well, that's now 0 because I've reached the ground. Right, down here, ground level. That's where I want to find the speed. And my kinetic energy, well, I don't know what it is, but I know it's equal to 1/2 m and then the final speed squared, and that's the thing that I want. So I could just say, well, do I set this equal to this and solve? No, that would not be right. Why not? Because there's an interaction I haven't taken into account, namely friction. As I go from here to here, right, energy is lost to friction. how do I find this? I'm going to use work, because friction is a non-conservative force, so I can't use a friction potential energy, right? It's not a thing. Well, let's figure out the work done by friction. The work done by friction is equal to, well, the force of friction times the displacement. Now, if I look at this situation here, right, the displacement is from up here down there, and throughout this journey, friction just opposes the direction of motion. So my force is going to be always the opposite direction. I can just write it like this. Minus, I'm going to write the force of friction right away in the way I figured out before, mu k times mg cosine theta. So I do need to know that part, how to express friction in terms of the other quantities, times L. Let me just annotate that for you. This is the magnitude of the friction, what I called F subscript k before. This is, if you like, my delta x. Of course, this being the normal force, this being the coefficient. The minus sign comes from the fact that they're pointing in opposite directions, right? The delta x is this way, but the force of friction is the other way. And so the force of friction is negative if my x direction points downwards. If positive is down the hill. This is the work done by friction, and again I could actually rewrite that knowing what L is, the same thing as before, mu k times mg cosine theta, and then L we had as h over sine theta. That's just from the geometry of the setup. This was the same logic as before. So there's an overlap between the two methods for sure. So now what I can say is, well, the final energy in total is equal to the initial total energy minus the amount lost to friction. Right, so let's write that down. So the final total energy is the initial total energy minus the energy lost to friction. Now I said a minus here, but the minus is kind of already included here. So I could also write this, and that includes the minus sign, as the work done. So I'm adding the work done by friction to my total energy. But because it's negative, I'm really subtracting a certain amount of energy. You shouldn't get confused about the signs, right? I know it's negative, and indeed it is negative here, but it's only one minus sign in total. Right? So that's why I'm saying it here. You could write plus equals plus the work done by friction, but this is a negative quantity like we just figured out. Right? This is the value in red from above. Okay, so now we can put the pieces together. Right? I can write the final total energy was just 1/2 mv squared. There was no gravitational potential because we're at the bottom of the hill. Initially it was all gravitational potential, but those are not equal because in the process work was done by an external force that doesn't have a potential energy. That external force was friction, and the work done was negative. It was equal to minus mu k mg cosine theta times h over sine theta. All right. We can simplify this a little bit, right? I can cancel out the m's. And maybe I can factor out the h and the g. So I have 1/2 v squared equals gh times 1 minus mu k cosine theta over sine theta. And so, well then, v squared is just twice gh 1 minus mu k cosine theta over sine theta. And at this point I could just plug in the values and find v. Notice that this matches what we had before, right? In our previous solution we found this expression here. And here we wrote it as one fraction, sine theta minus mu cosine theta over sine theta, but sine theta over sine theta is 1, and then so I could have split up the fraction. That's the form we have down here. So let me see if I can show them to you at the same time, right? It's this expression here that matches exactly this expression here. Should have called this v final, of course. That's what I labeled it throughout. And so you can see how I get to the same answer, right? Now I plug in values, and again you can try this out. It should come to 54.06 meters squared per second squared, because it's exactly the same expression as before. So 2 ways to arrive at the same result: via forces or via energy and work. Which one's faster? I don't know. About the same, really. Are there any other advantages to each of the methods? Well, when there is an external force that requires work, the energy route isn't as efficient as it is when it's all about just energy conservation, right? Then that is definitely the better way to do it in many cases. Not always, but in many cases. In this case, they both take about the same amount of time. One advantage of using the force method, actually, the old one, is that if I wanted to find the time to the bottom, for example, I get it more easily out of this, because I have the acceleration. I can just start here and then find the time it takes to the bottom. If I want to find the time it takes to the bottom using energy, well, I'd have to find the final velocity and then use kinematics to work backwards from there. It probably takes a little bit longer in that case. But every situation is different, and you want to have both tools available to you, like both methods, so when you encounter some new problem, you can use either one of the methods to solve it. And there may be situations where one of the two, where using forces and so on, is really tricky and complicated, energy is really fast. And there's situations where it's the opposite. So both of them should be in your toolbox. See you in the next lecture.